I've been fortunate to have to work with Shon in two different areas. First of all, Anne and I were research students of Shon's in the mid-1970s, but also Shon has had a long and distinguished relationship with Rolls-Royce over many years. So I'm going to talk about prospects for reducing aero-engine noise. Over the past 40 years, significant reductions in aero-engine noise have been achieved from the early turbojets of the 1950s and 1960s. This has largely come about because of the increase in bypass ratio of the high bypass ratio turbofan, but has also required detailed, careful attention to the component design, and also increases in improvements in aircraft performance. The dominant sources of engine noise are fan noise. These are tones associated with the rotor on its own when it's traveling supersonically at the tip, and also due to interactions of the rotor with, for example, the stator. And also associated with that is buzzsaw noise, which are lower frequency tones due to blade-to-blade differences associated when the fan is rotating supersonically. And then broadband fan noise, which is becoming one of the most important sources on current engines. There's jet noise, which is, again, a broadband noise source at low frequencies for most civil applications. Compressor noise, high-frequency tones. Combustor noise, a low-frequency broadband noise. And turbine noise, again, high-frequency tones. But it's normally fan and jet and airframe noise that dominate the aircraft signature. The changes that have occurred between a turbojet of the 1960s design and a typical modern high bypass ratio, because of the increased diameter and the reduced jet velocities, there have been very significant reductions in jet noise. Here the size of the lozenge indicates the level of the noise, and the direction indicates where the noise peaks. So we've seen very significant reductions in jet noise, and compressor noise also has been reduced slightly. Turbine and combustor noise, again, careful design has reduced those. But on the modern turbofan, you also have the noise due to the fan, both radiating out of the intake and radiating out of the bypass nozzle. And this is becoming one of the most important sources. Looking in more detail, these are the noise sources of a typical modern aircraft at the approach to landing condition. Here again are the engine components. And what we have across here is showing you the different elements and their relative magnitude. This is at 60 degrees to the engine inlet. So this is when the aircraft is approaching you. And we have fan noise radiating from the intake being the dominant source. Oh no, airframe noise there is a dominant source. Fan noise from the intake being the second one. Fan noise from the exhaust even radiating around into the forward arc. Jet noise, the installation effect on jet noise, then some combustion noise, turbine noise, and compressor noise. And what we've plotted here is the vertical axis is the frequency of the sound, and the horizontal axis is the time of as the aircraft is approaching you and going over. A yellow is the highest noise levels, and blue the lowest noise levels. And you can see, this is the overhead position. This is actually 1 second before overhead when we're at 60 degrees to the inlet. And you can see some tones present here. This is the tone at blade passing frequency. And because of the Doppler shift, it isn't at a constant frequency, but it reduces as the aircraft goes over. You can just see 1, 2, 3, and 4 BPF. Now, as we go through to the rear arc, noise from the green rearward fan noise, the combustion noise, and the turbine noise increase slightly. So if I show you what happens at the approach condition, you see the forward fan noise initially dominating, gradually reducing as the aircraft flies over. You might be able to hear the high tone from the turbine. play that again once, I hope. No, without the sound this time.
The plane's gone.
That's right.
This is the new suppression.
Okay. Proprietary, going to a higher speed at a takeoff condition when the aircraft's following a flight path where it cuts back to reduce noise over the community. In this case, the jet velocities have increased, and so jet noise now becomes more significant. And you can also hear the buzzsaw tones ring very significantly in the forward arc. But the jet noise has increased, but again, fan noise, combustion noise, and turbine noise contribute. Airframe noise is not so significant at that condition. Shall I try it again? No, go to full. Right, so at full power, this is where the jet noise dominates. So, Rolls-Royce is pursuing targets for reducing noise, both for Vision 10 for aircraft entering service in 2010, and also Vision 20 for those entering service in 2020. And the typical solutions for a 2010 engine is refining the existing architecture and what one would call Generation 1 noise technologies, that have been developed for example, in European and in US research programs over the past 5 to 10 years. And the Trent 500 powering the Airbus A340, the Trent 900 powering the Airbus A380, and the Trent 1000 powering the Boeing 787 have all actually introduced higher bypass ratios as being one of the methods of reducing aircraft noise significantly. This is the average decibel reduction relative to a typical aircraft for the year 2000, averaged over the 3 conditions. Increasing bypass ratio then is one of the effective methods of reducing aircraft noise and jet noise, but also a nozzle lip treatment, serrations, are a method of reducing jet noise. And this here we're showing you the nozzle serrations that were tested in the Boeing Rolls-Royce Quiet Technology demonstrator a few years ago. Serrations work by inhibiting the growth of axisymmetric instabilities on the jet. What you can see here is the turbulence levels in the jet downstream of the nozzle, both in the datum nozzle and in the nozzle with serrations illustrated below. And what you can see is that with the serrations, the levels of turbulence levels further downstream in the jet are significantly reduced from the high red levels in the datum nozzle. And this equates to, here we have a frequency versus sound pressure level at different angles to the jet. And you see the significant reductions in jet noise at those low to mid frequencies due to this reduction in turbulence downstream because of the serrations. But also you might be able to see potentially some increases in turbulence close to the nozzle here. Just a little bit of red creeping in there. And that can result in an increase in the high frequency noise. And careful design is always required to get rid of that high frequency. In addition to reducing noise, those serrations can increase the drag and hence the fuel consumption. So what you're really after is deployable serrations that you have present as you take off, but retract as when you are in cruise to reduce the fuel consumption in cruise. So you have serrations in present at takeoff and reducing in cruise. And this is showing some smart materials where the serrations here are effectively, this is where they are at the higher temperatures, they're deploying at the takeoff and climb. But as you get to lower temperatures, more appropriate for cruise, although you'd have to adjust the materials to make it work in that case, it goes to back to the retracted position. So the next generation of serrations might well include smart materials to reduce the impact on fuel consumption. Moving on to fan noise, CFD techniques are being used to design low noise, high efficient fans. What we have here is a fan blade, green there, which twists, and the tip of the fan blade is along the top there. And we have a CFD prediction at the top there, and a mesh at the horizontal plane in black there. So by parameterizing the key the features of the fan blade geometry, and then automatically generating your mesh around that geometry, subsequently running CFD to produce both the noise and the aerodynamics, and then from that deducing a cost function in terms of the radiated noise. You can then go around with an optimizer, varying the design parameters to optimize the fan. And here you see, with a number of iterations, how that optimizer has reduced the noise from the fan design. It gradually reduces down, but clearly at some stages the optimizer has gone off on a red herring and the noise has increased. But eventually you reach a stable design with a significant noise reduction. This is an example of the kind of blade you might come up with where it's swept at the fan tip. And here is the CFD. This is a datum fan compared to the low noise fan. And one of the features you've done with this design is that the shock, which previously is an expelled shock here, has now been swallowed by the throat. These are the fan blades, the three fan blades there. They've been swallowed into the passage between the fan blades and hence makes less noise. And when you have blade-to-blade differences, these can result in uneven shocks. This is a very exaggerated picture of the kind of typical blade-to-blade differences you get because of the manufacturing process in a turbofan. And because of these differences, the shocks themselves differ in magnitudes, and as they propagate up the intake, the stronger shocks catch up the weaker shocks, and from a fairly regular pattern near the fan, it comes to quite irregular shock pattern further up, and that introduces lower harmonics, not just the blade passing frequency, but noise at every engine order frequency. And what we've plotted here is both the CFD prediction in red and the measured data in purple, showing the spectral variation in noise. This is the blade passing frequency, twice blade passing frequency, and its third harmonic. But you also see the tones at the engine, or the buzz tones at the engine orders, and you can see that CFD is able to predict their character. Another way of reducing fan noise is to improve the intake, for example. Traditionally, because of the problems of manufacturing, intake liners have had splices and are not continuously lined all the way around the intake. Here, in this picture, this is a Trent 800 intake, and the white line there denotes the limits of the acoustic treatment. So there's a hard wall splice there, and there's a hard wall section there, which is an inlet. In the Boeing Rolls-Royce Quiet Technology Demonstrator program, we also flew an intake which had a very much reduced liner splice there in order to reduce the noise going out. And we've also repeated that in the European Silencer program, with Airbus. I'm not, let's see, what I'm going to try and, no, sorry. That's the noise, the original intake. You've very much taken out some of those annoying tones by getting rid of the liner splices. Now, the reason why liner splices are so bad for aircraft noise is because the tones at blade passing frequency and buzzsaw tones, the energy is generated very much in the azimuthal mode number equal to the engine order you're looking at. So if you've got, say, a 13-bladed fan, you have here the energy with azimuthal order that is generated by that fan, and here it's clearly all generated in the azimuthal mode number 13, the first radial mode number, because the other radial mode numbers are cut off. And the energy so is very much just in that one mode. And because the fan is only just going supersonically, the acoustic liners are very efficient in attenuating that sound. And what we've done here is an acoustic model where blue is the acoustic liner, and we've got yellow hard wall areas going upstream and downstream of the liner. And we're going to propagate sound through this model of the intake. And you see here the sound that comes actually at the intake inlet. Now what I'm going to then do is put in some yellow hard wall splices across the liner, and you'll see the mode shapes varies very significantly from what they are in this initial case. So as the splices increase in width, the mode shape changes dramatically, but compared to the zero splice case, you immediately get a very rapid increase. For very thin, very small splices, you'll get a very, oh no, we'll move on then. You get a very significant change in mode structure. Oh, I hope we'll move on. Oh, right. Another way of reducing fan noise is to look, is to line the intake lip. What I'm showing you here is a computational aeroacoustic calculation of noise propagating out of an inlet. Here's the fan blade. There's the nacelle, the intake. Here is the spinner, the center of the engine. And in this area here, there's a finite element calculation. Outside this, it's an infinite element calculation to take the sound to the far field. And we've got three cases here: hard wall, a lined barrel, and then a lined lip as well as a lined barrel. And underneath, you have a magnification of the area close to the lip. And because of the higher the overspeeding, the higher Mach numbers just close to the liner lip, you get significant shortening of the wavelengths there. And so because of that reason, the liners in this region are very effective in attenuating the sound. You see in the hard wall, a lot of the sound comes out. This is reduced significantly by the lined barrel, but it's almost reduced even significantly further once you line the lip as well. Around about a few years ago, the leaders of aviation in Europe got together to put together what their vision was for the aviation industry in the year 2020. And they were looking to reduce CO2 emissions by 50%, reducing NOx by 80%, reducing the perceived noise by half, and eliminating the noise nuisance outside the airport boundaries, substantial cuts in operating costs, fivefold reduction in accident rate, drastic reduction in the impact of human error, 99% of flights within 15 minutes of timetable, could be good. New standards of quality and effectiveness, halving the time to market from an aircraft launch to its reaching the entry into service, and also improving the synergies between civil and military research. And they had this vision of that by 2020, this is what the aviation industry would be producing. But it was not just, because it's not just the noise, quite often, in order to reduce noise, you penalise other aircraft attributes. For example, going to higher bypass ratio potentially increases fuel burn. So we have not just to reduce all the environmental bad aspects of aviation, like noise, emissions, and fuel burn, but we need operating costs, aircraft performance, and the business case. All those things have got to be simultaneously developed to meet the ACARI goals. With the current technology and further evolution of aircraft, it's unlikely that one will not achieve that goal. And the Vision 20 requires a technology breakthrough which will come through Generation 2 noise technologies, novel architectures, and advanced operational procedures. So Generation 2 noise technologies includes items like, for example, active flow control to reduce fan and jet noise. Novel architectures that are being looked at include going to even higher bypass ratio engines and novel aircraft configurations. Now, many of these novel airframe and engine architectures will require the development of enabling technologies outside acoustics. For example, to go to higher bypass ratio engines, you require lightweight, low-drag nacelles, really more than any acoustics research. So there's a lot of enabling technologies outside acoustics that need to be developed to meet these goals. The second item was advanced operating procedures. And what's illustrated here is an advanced continuous descent approach, where instead of going down in stages before landing, the engine power is kept at a low level so that it is continuously descending into the airport, and also turning, if you like, as well, in order to avoid areas of community which would otherwise be under the flight path. And also you can increase the rate of descent, steeper descents, in order to increase the height of the aircraft over the population and hence reduce the noise. But the major requirements to develop this really is advanced air traffic management more than necessarily the technology for the aircraft. So in summary, technology has delivered major reductions in noise, but further progress will require sustained investment and substantial progress in reducing the many different complex noise sources that contribute to the aircraft noise signature. Our industry is conducting comprehensive noise research programs, especially in Europe and the US, involving research establishments and universities, and many promising concepts for reducing noise are being developed. But further work is required to prove and develop the ideas for application in the very demanding aero-engine environment. Thank you.
Pretty good, Andrew. Let me ask you this. In the future, there's still going to be a need for engines that have bypass ratios of 5 or so for domestic aircraft.
Well, traditionally, the higher bypass ratio engines have initially seen service in the long-range large aircraft, but they have trickled down into the sort of the medium, shorter range. The economics of long-range and short-range aircraft are different, so that they could be potentially different, and we could see a return to propellers in the shorter range aircraft as well.
May I ask you a couple of questions? In Rolls-Royce practice, is it the industry practice with respect to low bypass ratio engines? These acoustic tracers can be used for identifying the component in distress and then take active corrective action. For example,
in low bypass ratio engines?
Yeah.
What was the second half of the question?
Component in distress. For example, fan may go to surge mode. By acoustic tracers can it be detected and then the corrective action can be taken.
Measure the acoustic signature.
Yes.
Oh, right. Okay, sorry. So the question is, can you use the acoustic signature to,
Right.
to determine when the fan blades are deteriorating? Yes, you can use many acoustic and vibrational signals to aid you in the in deciding when you need to pull an engine, when you need to take an engine off the wing, or when you need to change that. And much more now, there is online assessing any maintenance requirements before the aircraft even lands. When it's in flight, you can work out what is required when the aircraft lands.
The next question is, do these give sufficient information for acoustic fatigue and study of this?
Well, I don't think at this stage you would be using just the acoustic measurements to replace the other methods of looking at for examining the fan integrity. I don't think it's not something I think you can rely on at this stage, but it's started. Such measurements are starting to give you us useful information.
Thank you.
All right, any other questions?
Andrew, you showed the component breakdown as a function of time as the airplane flew over an observer location. I'm curious as to the degree of confidence in this breakdown that one has as the angle of observation is varying.
It's not something that you could easily measure. You deduce the breakdown by a variety of testing and theoretical methods. For example, we have rig test results where we're only looking at fan noise. So from that we can understand the characteristics of fan noise. We can do things with and without acoustic liners on an engine, and you can tell perhaps from that what noise is coming out of the intake. You can use source location techniques to try and discriminate between jet noise downstream of the nozzle and the core, the nozzle and noise coming out of the core. But it is subjective, and a subjective interpretation is quite often involved, and engine and airframe manufacturers do not always agree on the relative components of noise.